Hello everyone, I'm Rajasri, Assistant Professor, Department of EEE, working at MLR Institute of Technology, Hyderabad. And in today's lecture, I'll be teaching single-phase half-wave controlled rectifier with R load. And this is the circuit diagram of single-phase half-wave rectifier with resistive load. And here if you see, here we are making use of a thyristor. And usually we make use of a diode. And if at all, if we make use of a diode, in that case, let me draw the circuit diagram. If at all, if we are making use of a diode, in that case, the circuit diagram looks like this. This is the diode, AC voltage, and this is the load. And if at all, if we are making use of a diode, say for example, I am providing an input voltage of say 10 volts. In that case, output voltage will also be 10 volts, excluding certain amount of drop, and that is usually negligible. And if at all, if we are making use of a diode, once it is forward biased and once it starts conducting, in that case, it gives same amount of output voltage, whatever we have applied it as the input. Because diode has no control over output voltage. In this scenario, thyristor came into picture, and the whole purpose of thyristor is in order to provide the control output voltage to the load. So that is the idea behind. We can make use of, we can control the output voltage using the thyristor by making use of firing angle. By correcting the firing angle, at that particular instant, we can trigger and thereby control the output voltage which is actually fed to the load. And here, if you see, what is the basic purpose of a rectifier? That is, rectifier converts AC to DC. So here we have input voltage of AC, that is, it has got both positive half cycle as well as negative half cycle. So during the positive half cycle of the input voltage, the polarities across the thyristor will be positive and negative. That means right now thyristor is in the forward blocking state. That is, what does it mean by forward blocking state? That is, it is ready to conduct but not at conducting state. That is, unless and until we provide a triggering pulse, gate triggering pulse, the thyristor will not conduct the current through the load. So at this instant, see, right from 0, the thyristor has come into the forward blocking state, and at this instant, here we are providing the firing angle of value alpha. In that case, the thyristor started conducting, that is from alpha to pi. We are getting the output voltage, that is from alpha to pi. See, right from 0, the thyristor is forward blocking state. It has got forward bias, but until and unless we provided the gate triggering pulse, so-called alpha, it did not conduct. The moment we have provided the triggering pulse, at that instant, it started conducting until pi. Why only till pi? That is, during the positive half cycle, if you see, during the positive half cycle, here thyristor will be short circuited. That is, it is conducting at this instant called alpha, it is short circuited, and thereby it started conducting current through the load. And that is how we are getting the output voltage right from alpha to pi. And the moment it reaches pi, what happens? The polarities will be negative and positive. That is, during negative half cycle, the polarities will be negative and positive, because of which thyristor will be in the reverse bias state. Thyristor now, it will be in the reverse bias state. So when it is in the reverse bias state, it acts as an off switch, or we can also call it as open circuit. This is the individual circuit diagram during the positive half cycle, during which the thyristor acts as short circuit. And this is the circuit diagram during the negative half cycle, during which the thyristor is in the open circuit, or it acts as a off switch, and here it acts as on switch. So the moment it reaches pi, at that instant, negative half cycle has been started. the polarities now across the circuit will be negative, positive, due to which the thyristor is in the reverse bias state. And at this instant, since it is open circuited or thyristor acts as off switch, there will be no current through the load. And that is how we are not getting any sort of output voltage right from pi to 2 pi, because thyristor is in the off condition. Again, during the positive half cycle, if you see, right from 2 pi, the thyristor will be again positive and positive, negative, but thyristor will be in the forward blocking state. The instant called 2 pi plus alpha, we started providing the triggering pulse, and at that instant thyristor, since it is on, it started conducting current from 2 pi plus alpha to 3 pi. And again, the moment it reaches 3 pi, negative half cycle starts, and because of which the thyristor is now in the off condition. Alright, so you may ask me, how is that we are getting the output voltage during alpha to pi? That is, if you see, when the thyristor is short circuited during the positive half cycle, since the thyristor is short circuited, whatever the voltage which we are applying across the source is appeared across the load. Whatever the voltage which we are applying across the source is what applied across the load. That is how we are getting the output voltage right from alpha to pi when the thyristor is under the on state, or we can also call it as short circuited. Or otherwise, I can also explain in this way, that is, the moment when thyristor is on or when it is short circuited, at that instant the output current I0 starts flowing through the load, and during which output voltage is equal to I0 into R. So that is how we are getting the output voltage when the thyristor is under on state. Alright, so whenever the thyristor is triggered, that is from alpha to pi, the current is flowing through the load during positive half cycle, and that is how we are getting output current right from alpha to pi. And if you see, this output voltage and output current waveform will be one and the same. It is because of the resistive load. Since I0 is equal to V0 by R, the shape of the output current will be just similar to that of the output voltage. And here it is again conducting, thyristor is again started conduction from 2 pi plus alpha to 3 pi. And that is how we are getting the output voltage right from 2 pi plus alpha to 3 pi. Whereas here, since the thyristor is under the off condition, there is no output current flow through the load. And coming to the thyristor voltage waveform. And here, thyristor voltage waveform, the voltage across the thyristor. See, we have already discussed in the initial stages, whenever the switch is short circuited, in that case, the voltage across the device will be less. And if at all, if the same device is open circuited, in that case, the voltage will be high. The voltage across the device will be high. And if you see, right from 0 to alpha, thyristor is under off state. And that is the reason the source voltage is appeared across this particular thyristor. Whatever the voltage which we are actually applying across the source, across the source is appeared across the device during its off state, because during the off state the voltage will be high, and that is how it is following the input voltage. And the instant right from alpha to pi, here the device has come into the on state, and the voltage across the device will be very less, that is equal to on state voltage drop of the device, which is almost negligible. So that is the reason, if you see, the moment when we triggered the thyristor, at that instant supply voltage has come down and it is almost zero. The voltage across the thyristor now is almost zero, and the moment it reaches pi, if you see here, thyristor is got turned off from this instant, pi to 2 pi plus alpha. So that is the reason from pi to 2 pi plus alpha, thyristor is under off condition. Whatever the supply voltage which we are actually feeding is applied across the device. So this is the voltage across the device, right from pi to 2 pi plus alpha. And again, at this instant, thyristor's positive half cycle is being appeared, and at 2 pi plus alpha, we are providing the triggering pulse. The thyristor is again turned off. So that is all about the working principle of single phase half wave rectifier with R load. We have seen positive half cycle as well as negative half cycle as well as waveforms. And coming to the average output voltage expression of single phase half wave rectifier with R load. If you take, we average output voltage is usually denoted with V0 average. V0 average, which is equal to, it is given by the general formula I have already discussed, 1 by T, 0 to T, V0 of omega T, V0 of omega T, d omega T. And if you see in the waveform, the thyristor, the total cycle is from 0 to 2 pi. 0 to 2 pi, the total time period. I mean, every similar cycle is repeating for 2 pi. So that is the reason here we are taking the output voltage time period as 1 by 2 pi. And if you see, the actual waveform is actually present from alpha to pi. That is from alpha to pi. So that is the reason here we are taking the limits as alpha to pi, where V0 is equal to V maximum into sine omega t d omega t. And here by integrating, that is Vm is constant, bringing it out Vm by 2 pi, and integration of sine omega t is minus cos omega t. It is conducting from alpha to pi. Substituting the limits, we get Vm by 2 pi. Upper limit is minus cos pi, minus of minus plus cos alpha, where cos pi value is minus 1, minus of minus plus 1. In that case, we get Vm by 2 pi into 1 plus cos alpha. There is nothing but V0 average. Average output voltage expression for single phase half wave rectifier with resistive load. Similarly, we will derive the output voltage expression for V0 RMS. So here V0 RMS is equal to 1 by T, 0 to T, V0 square of omega T d omega T whole to the power of 1 by 2. As we have already discussed, the total time period, that is every similar cycle, repeats for 2 pi. So that is the reason the total time period is taken as 2 pi, and it is actually conducting from alpha to pi, where V0 is Vm square sine square omega T d omega T whole to the power of 1 by 2. If we resolve this expression, Vm square constant, bringing it out, Vm square by 2 pi, and in order to integrate sine square, let me write it as 1 minus cos 2 omega T by 2, integration, that is from alpha to pi whole to the power of 1 by 2. And if you resolve this, let me take this 2 denominator outside. In that case, we get Vm square by 4 pi, and integration of 1 is omega T. It is conducting from alpha to pi, minus integration of cos 2 omega T is sine 2 omega T by 2 within the limits alpha to pi whole to the power of 1 by 2. In that case, we get Vm square by 4 pi, substituting the limits, upper limit minus lower limit, that is pi minus alpha minus sine 2 pi by 2 minus of minus plus sine 2 alpha by 2 whole to the power of 1 by 2. This is the required V0 RMS expression for single phase half wave rectifier with resistive load. And then peak inverse voltage, that is nothing but the maximum voltage which will be appeared across the device in the negative reverse bias condition. So in that case, peak inverse voltage, it is given by the formula. Peak inverse voltage will be V maximum. See, when the thyristor under reverse bias condition, the voltage which is appeared across the waveform is Vm sin omega t, is it not? And the maximum voltage can be appeared at omega t is equal to pi by 2. Pi by 2 in the sense 90 degrees. Sin 90 will be 1. In that case, the peak inverse voltage for single phase half wave rectifier with resistive load will be V maximum. This is the formula. Circuit turn off time, the duration at which the thyristor will be turned off, that is omega t is equal to, it will be turned off from the instant 2 pi to pi. Half wave rectifier, it will be turned off from the instant 2 pi to pi. So in that case, the omega t is equal to pi. We get circuit turn off time Tc is equal to pi by omega. This is the formula for circuit turn off time. Similarly, input power factor. Input power factor, it is given by the formula V0 RMS into I0 RMS by Vs into Is. And if you see the circuit diagram of single phase half wave rectifier, there is only one loop, that is same current will be flowing throughout the circuit. So in that case, I0 RMS is equal to Is. So these two gets cancelled. And finally, input power factor is equal to V0 RMS by Vs. So here, if you do V0 RMS by Vs, in that case, we get input power factor as, let me rewrite this equation, V0 RMS is equal to whole to the power of 1 by 2. I am applying whole to the power of 1 by 2. In that case, Vm by 2 root pi, and this remains same, pi minus alpha minus sine 2 pi. Sine 2 pi value is 0, 0 by 2 is 0, and this becomes plus sine 2 alpha by 2 whole to the power of 1 by 2. This is nothing but our required V0 RMS expression. And here, V0 RMS by Vs gives us the input power factor. And for that purpose, Vm is nothing but, we can write it as root 2 into Vs. And here, root 2 and 2 gets cancelled. We get Vs by root 2 pi into pi minus alpha plus sine 2 alpha by 2 whole to the power of 1 by 2. This is nothing but our input power factor expression. In the next upcoming lecture, we will see single phase half wave controlled rectifier with RL load. Thank you.